Hi everyone and welcome to this new video about steady state analysis. We continue with RLC circuits. In this example I will consider again the superposition principle with a little bit complicated circuit. So that's our example number 6. What we did in example number 5 was also using the superposition principle with a relatively simple circuit. And this circuit we have a little bit complicated situation with different sources and also more components. So actually the situation is a little bit complicated. So that will be also challenging. Also we give you more background in the analysis using the superposition principle. So what do we have? We have two inductors, L1 and L2, one resistor and one capacitor, one voltage source, Vs, and one current source, IA, both in time domain representation as shown here. And we have also a question, which is the calculated steady state capacitor current IC, which is in this direction. So how do we start? As we did also in the previous examples, we first transform all of the elements in the frequency domain, then we carry out the analysis and we activate, of course, one source at a time, because that is the superposition principle. So let's start first with the XL1, which is the reactance of the inductor L1, which is the omega times L1, and omega here is here 1000, 10 to the power 3, times the 7 times 10 to the power minus 3, which is the 7 millihenries for the L1, and this will give us 7 ohms. If I now move to XL2, which is omega times L2, which is 10 to the power 3 times 8 times 10 to the power minus 3, which is 8 millihenries, will give us 8 ohms. Now for the capacitor, X of C, which is 1 over omega times C, which is 1 over 1000, and capacitor is 200 microfarads, will be 2 times 10 to the minus 4, which is exactly the same, and this will result in 5 ohms. Now for the sources, I have the Vs, which is in cosine representation, so I can take over the amplitude 100 and all the phase. Phase is just 0 degrees in this case. For IA, the current source, also in cosine representation, so I will take the 4 amperes as the amplitude and the phase in this time plus 70 degrees, and of course in amperes. Okay, so that's actually the situation. So we can start the analysis using the superposition principle. I will now activate only Vs, so only Vs active. What do I have if I activate only Vs? This will be an open circuit in this situation, so this is only active. So we have actually no connection from this point to ground. You will still have the L2 connected to R2, and these together will be in series, and these together will be again parallel to L1. So I will have the following situation. So if I now redraw the circuit, I will have the Vs still in place. I have the inductor L1 and I have the capacitor C, and if I now place the resistor and the inductor in series, I have the following situation. This is L2, this is the R. So I have actually this circuit. This is actually the simplified circuit. What I would like to know is the following. I will of course want to work towards the current through the capacitor. One of the ways to calculate the current through the capacitor in this form, so due to Vs only, is calculate the total impedance actually seen by the voltage source Vs. So before I can do that, I will first simplify this expression for this. So R and L2 will make an impedance, so I will denote this as Z1. So I will make this together. This will be Z1 for me. And for the other one, for combining also the Z1 with the L2, I will make that Z2. So I will start first determining the Z1, which is R plus J XL1, and I know R, which is 10, and I also know XL1, which is I have an XL2, is this, sorry, so that will be 8. This will be in ohms, of course, and if I now convert this to polar representation, this will be 12.81 phase 39 degrees in ohms. If I now want to calculate Z2, this is just the parallel combination of XL1 and Z1. That will result in JXL1 times Z1 divided by JXL1 plus Z1. That's the formula for parallel combination of two components. Now, for this, it is better to use the rectangular representation, so I will use J and XL1 was 8 times the 10 plus J. XL1 was 7, excuse me, so it was 10 plus J8 divided by, and then the J will be here 7, J7 plus 10 plus J8. Now if you now simplify this, you will have for the Z2, if I move a little bit to the right, so you have minus 56 plus J70, that's for the first one, and you will have there 10 plus J15. Now if you now convert this to the rectangular representation, so if you simplify this, you come up with a rectangular representation. It will be 1.51 plus J 4.74 ohms. Okay, that's actually for the impedance Z2, which is now in series with the capacitor. So I have a total capacitor, so total impedance. So the total impedance seen here is Z2 minus JXC, which is 1.51 plus J 4.74 minus J5, which will result in 1.51 minus J 0.26 ohms. Okay, what is the next step? Now, if I now calculate the source current, just due to the Vs, so the current supplied by Vs, I also know the current through the capacitor C, because that's in series. So if I know I of S, which is actually supplied here, this is actually the I of S, which is IS, which is actually the capacitor current, and that is the voltage Vs divided by the total impedance seen by the voltage source Vs. That means if I now convert also this, so if I now also convert this into a polar representation, that will allow me to calculate the value of IS directly, or an IC directly in the polar representation. So what is the representation of the Z total in the polar representation? That will be 1.53, and the phase will be minus 10 degrees, and of course in ohms. Okay, let's move on. That will be 100 phase 0 degrees divided by 1.53 phase minus 10 degrees, and this will result in 65.4 phase plus 10 degrees, and this is the value of the capacitor current due to Vs only. So the effect of Vs only will result in this current, this capacitor current. Okay, if I now move to the second part, which is the effect of the current IA, so I will disable this, it will be a short. If I short this, what you see is the L1 will be parallel to C, and the R will be parallel to the the current source. So we have a couple of situations, so I will combine them together and I will make one diagram. So if I now activate only, so make it in blue, so only IA active. So what do I have? I have the following circuit. I have the current source IA, and parallel to that we have the resistor in effect. Maybe I can draw the resistor in the usual symbols. So this is the resistor. Okay, we have the inductor then connected to that, that's the L2, and we have the capacitor and the inductor L1 in parallel. So I will move up again to show you why this is correct. So let me check this again, let it zoom out. So we have this connection, as you can see, the IA is connected directly to L2, and then C and the L1 will be parallel, and R will be parallel to the current source IA, actually, which is shown here. Okay, if I now designate several points here, that will be helpful in the analysis. So I will make this point P, and this point I will designate as Q. What I want here is I will do two things. First is I will transform here, make a source transformation. So I will, let me write it down in a more clean way. So this is the IA. So I will transform this. So this will be transformed using source transformation from the Norton form. This is Norton. I will transform this in Thevenin form, and I will transform this, make this one impedance. So I will make this impedance, for example, impedance Z of P, and I will transform this to the Thevenin form. So we have here source transformation. So you have to do a couple of things. First, start with the Z of P, which will be shown here. Z of P, which is of course again minus JXC in parallel with JX of L, which will be minus JX of C times JXL1 divided by minus JXC plus JXL1. And this will result in, if you do the math here correctly, you will have minus J5 times plus J7 divided by minus J5 plus J7. And this will result in Z of P will be 35 divided by J2. And this will result again in minus J 17.5 ohms, or you can also make it in the polar form, will be 17.5 phase minus 90 degrees, also in ohms. So we have the representation for ZP. Okay, let's move on. Source transformation, that's also important. So how do we do the source transformation? The source transformation is actually the following. You have the Norton form, which is this IA parallel to the resistor R, and this is just point Q. I will now transform this to the Thevenin form, which is the voltage VA. I make now voltage VA in series with the resistor and connect it again the same point Q, which is mandatory, and that's the R. So how do you calculate VA? Now, VA is actually very simple, just Ohm's law. So if I want the voltage, which is resistor times the current. So of course in the Phasor notation, so I will have VA will be R times IA. So IA I already know, so I have the following. This will be 10 phase 0 degrees, and this will be 4 phase 70 degrees. So that will be VA will be 40 volts, the phase orientation of 70 degrees. So that's actually for the voltage source VA. Of course, you can convert this in a time domain, but that's not necessary in this case. So what we have is the following. You have actually this part converted to a series combination of the voltage source and the resistor. It is in series again with the L2, and that one is in series with the ZP. So we have simplified the situation quite a lot. And it will be handy when we carry out the calculation. So we are actually the following. So we have the VA in series with the resistor R, and in series with that is the inductor L2, and with that is the series combination of the impedance, which is ZP. So that's actually the whole business, and these are the points still valid. This Q, so this Q, and this point is P. Now, if I want to know again the capacitor current, I can determine the voltage actually at this point. If I know the voltage at this point, I also know the voltage across the capacitor. Now, again, using Ohm's law, I can calculate the capacitor current. So I would like to use the current divider rule here. So I would like to say Vp is equal to Zp divided by the total impedance seen by the voltage source Va, which is R plus J XL2 plus Zp, and then times Va. So what is Zp? Now Zp already calculated here, which is shown here. I will take this form, so I will have 17.5 phase minus 90 degrees divided by R is 10 plus J 8 plus, and I will this time take the rectangular representation. That will be handy in addition, so minus 17.5, and this will be 40 phase 70 degrees. Okay, now if you simplify this further, you will have 17.5 phase minus 90 degrees divided by 10 minus J, because this will be J8 minus J 17.5, that will be J 9.5, and a phase 40 will be 40 volts with a phase of 70 degrees. If you again convert this to polar representation, that will be handy in the analysis for division. That will be 17.5 phase minus 90 degrees divided by, that part will be 13.8 phase minus 44 degrees, and I am almost done, 40 phase 70 degrees, and this will result in 50.7, the phase of 24 degrees in volts. And this is also the capacitor voltage. So I will make it clear, this is also the capacitor voltage. Now the capacitor, because it is the combination of the capacitor and the inductor here, and the capacitor is in parallel, so we have the capacitor voltage also. Then we can now say the following. Then I can say that IC, which is VC divided by minus JXC, that's just the reactance of the capacitor, will be 50.7 phase 24 degrees divided by, and if I now convert this directly in the polar representation, will be 5 phase minus 90 degrees. So what do I have is 10.14 phase 114 degrees, of course in amperes. And this is the situation due to IA only. Now I have now partial effects. So partial effects, I have the Vs, what is the effect of that to the current capacitor current, and also the capacitor current due to the current source IA. So the net effect, total effect, will be here, total effect. That result will be the following. IC will be IC divided by IC due to Vs plus IC due to the current source IA. And this is of course just taking the values we already calculated. So what we have is the following. You have 65.4. You might ask, where is that 65 coming from? It is here, so let me move up. 65.4 in a phase of 10 degrees. That's actually due to only Vs. And we will take also this and combine them together, add them up, and it's actually the final result. So 65.4 phase 10 degrees plus 10.14 phase 114 degrees. If you want to combine now these two, of course you have to convert again to the polar the rectangular representation, combine the real parts, imaginary parts, again convert this to polar representation. So what we have is the end result is 63.7 and the phase will be 19 degrees amperes. Now I would like to, of course, go to time domain. So transform back to time domain. The time domain representation will be IC in time will be 63.7. That's just the amplitude. And again the cosine, again 1000 t, and this time the phase is 90 degrees. So what you recognize is you will have always the cosine and the 1000 radian per second times t. That is actually your template. Your amplitude is this one, and your phase 90 degrees is this one. And that's actually for the capacitor voltage using the superposition principle for this example. Okay, so this is actually your second example about the superposition principle using for the RLC circuit. Alright, see you next time, and don't forget to share and like, and have a nice day.